For this problem, we're going to do an existence and uniqueness proof, but it's going to be mixed in with a couple of universal quantifiers and a conditional. Here it is. Prove that for every real number x, if x is not equal to 0, then there's a unique real number y, such that for every real number z, zy equals z over x. Now that is definitely a mouthful, but it's actually quite an intuitive statement if you think about what it means. Right? So for every real number x, if x is non-zero, then we can find a y such that for every z, this equation is true. Now what does this equation amount to? If we just move the z over x over to the left side of the equation and factor out a z, then we see that the only way this equation can be true is if z is 0 or y equals 1 over x, right? Okay, and we're basically assuming that x is non-zero, so such a value for y exists, and we need there to be a unique real number y such that for every real number z this is true. Okay, now z equals 0 is not going to be true for most real numbers, and so for all of those non-zero values of z, this equation is going to have to be true. All right, and so there is a unique value of y that works, namely 1 over x. Okay, so we can make some sense of this, but we have a little bit of work to do to give a rigorous proof of it. Okay, so here is the statement: for all real numbers x, if x is non-zero, then there exists a unique y in R such that for all z in R, zy equals z over x. And we begin by letting x be an arbitrary real number, and then to prove the conditional, we assume that x is non-zero. And here is our existence and uniqueness proof. Okay, so that becomes two parts: existence on the first line, and then uniqueness spread across the next two lines. And let's take those two goals one at a time. First, we'll work on existence. And so to show that there exists y in R, such that this works out, we should decide what we think y is. And we decided it was 1 over x, right? If you replace y by 1 over x here, you can also see that you get z over x on both sides. So that's my guess, y equals 1 over x, and I have to check that y is a real number and that the remainder of this statement is true, namely that for all z in R, zy equals z over x. And so, well, we can take care of y being a real number right away, because x is a non-zero real number, and the reciprocal of such a thing exists and is another real number. And so we're just left with this goal, and we can let z be an arbitrary real number, and we just have to prove that equation is true. And, well, we're done with that, because if y is 1 over x, then we can replace the y here by 1 over x, and we get that this is true. So that takes care of existence. Let's pause that work and write up what we have so far. So we let x be an arbitrary real number, and we want to prove this conditional, and we assume x is non-zero to leave us with that goal, which will become an existence part and a uniqueness part. So we can say let x be an arbitrary real number not equal to 0, and we're going to show that there exists a unique real number y such that for every real number z, zy is equal to z over x. And first we're going to prove existence. So how did that go? Well, we decided that y was going to be 1 over x, and we had a couple things to prove, and x being non-zero essentially gave us our first goal, that y is a real number, and then we had to let z be an arbitrary real number, and then we got that out of this stuff. Okay, so we prove existence, so we said let y equal 1 over x, and let me just say that that is a real number, hoping that my reader remembers that x is non-zero. You can put that in there again if you want to be sure. And then next we'll say let z be an arbitrary real number for that part, and we'll just say we see that I think I have that right there, that zy, which is z times 1 over x, equals z over x. Okay, so we've arrived at our goal. And that means we can go on to think about uniqueness. So here's the statement we got to prove for uniqueness. We begin by letting a and b be arbitrary real numbers, so I'll add them to x over here. And it leaves us with a conditional to prove. And we bring the antecedent over as a given, and that's a conjunction, and I don't have a lot of space here, so I'm going to go ahead and break that up into two givens right away, and we're just left with a equals b as our goal. And in order to get a equals b, we have to be a little bit clever here. We know that these equations are true for every single value of z, and if we want to get just a and b, why don't we just plug one in for z? Okay, that's actually universal instantiation, right? We're allowed to take this to be true for any particular real number z that we want. So just let z equal 1, and we get a and b both equal to 1 over x. And from that, we can certainly conclude that a equals b. So let's try to write that down. We said let a and b be arbitrary real numbers, leaving us with this conditional goal, and then we are going to take these two statements as givens and have our goal be a equals b. So I'll say next we prove uniqueness, let a and b be arbitrary real numbers such that these two statements are true, right? And so I can say for every z in the real numbers, za equals z divided by x, and zb equals z divided by x. So I've sort of just said this for all z and r at once, and then followed it up with those two statements. And our goal is to show that a equals b. So we show that a equals b. All right. And then finish up. We did a couple universal instantiations to get from these down to these statements, and that gives us what we want, a equals b. Okay. So I'll just say letting z equal 1. We have in particular that, referring back to these statements, that a equals 1 over x and b equals 1 over x, and it follows that a equals b as desired. Okay.